You may remember from grade 9 that current electricity is able to flow around what we call an electric circuit. And any circuit is really just made up of at least 3 basic elements. Some kind of source, like a battery or a wall outlet that can provide the electrical energy. Some number of loads, like light bulbs or any kind of electrical appliance that is using up some of that electrical energy. And then we also need connectors, which we know have to be some kind of conductive material, like metal wires, for example. From there, it's important to be able to understand circuit symbols because most electric circuits are represented through their basic symbol diagrams. And so some of these you would have talked about a little bit in grade 9. There might be a few that you've either forgotten and maybe a few that you didn't get to cover in grade 9. So this will just provide a good overall review. The first thing we could talk about is a single cell. And a single cell, a single simple source of energy that might be provided to a circuit, we represent like so, with just one small vertical line right next to a larger vertical line, and then the other horizontal lines that I've drawn are just the connecting wires that come from each side. That's how we represent just one single cell. But what we mean by a battery is actually a collection of multiple cells. And so we just draw that as a collection of multiple cells that we drew from our original cell circuit diagram. So that would be how we could represent a battery, just multiple cells that are all connected together. Moving over to the other side, a resistor is also a really common symbol. So a resistor is an example of a load, and it's actually the simplest kind of load. Its only job is to resist the flow of electrical energy and absorb some of that electrical energy. It really isn't used for anything else other than resisting and absorbing some of that energy. But it looks like this. We have our connecting wires, and then we just draw a jagged, spiky line, and then another connecting wire coming out from it. That's a resistor. And below, we can also draw what a lamp would look like. And there's actually a couple ways that we might see this. So one way you might see a lamp represented is something like so, with a little circle around it. You may also just see a circle with an X through it, and the connecting wires from either side. So either an X through it or something like a little bit of a squiggle with a circle around it that kind of looks like a light bulb. Either of those are the commonly used things for a lamp or a light bulb. A transformer is something I won't talk too much about now because they'll make a little bit more sense at the very end of our unit. We're going to talk about them in more detail then. But a transformer is something that can be used to drastically increase or decrease the voltage that's running through a particular circuit. And so for that, the symbol looks a little something like this. We've got a wire that's coiled up facing another wire that's coiled up as well. And so it almost looks like two fists coming together doing a little fist bump. But those are actually coiled wires that are brought close to one another. And again, we'll talk a bit more about why the wires are coiled and how that provides this increase or decrease in voltage. Towards the end of the unit, we'll get to that. The symbol for a motor is a pretty simple one. We draw our little connecting wires and then a circle, and we just use an M inside of the circle. That's for a motor. For an ammeter and a voltmeter, an ammeter, remember, that's used to measure current, and a voltmeter is used to measure voltage or potential difference. The symbols for those are really easy as well. So we draw our connecting wires and circle, and then we just have an A inside for an ammeter. And you'd probably guess now it's just a V inside for a voltmeter. So motor, ammeter, and voltmeter are all very simple symbols. We're just using the first letter of the word to represent them. We also need to be able to show switches. So a switch is just something that we can easily use to disconnect or reconnect the circuit. So we can allow the current to flow at certain points and turn it off at other points. So if the switch is open, it might look something like this. And it should essentially look like an open gate. The closed switch then looks very similar, except it's actually closed. And so it really just kind of looks like a straight line, but it's useful if you draw two little dots on it. And the two dots represent either side of the gate, and now it's closed. And so the switch has been closed, so it is really just one clean connecting wire now. But when that switch is open, it disconnects the circuit. A fuse is a special function inside of a circuit. And its job is to actually intentionally break the circuit if too much current flows through it. And we draw it as something like this. We'll draw our typical connecting wire, and then something like a little wave pattern, and then another little connecting wire coming off of it. And so that little wave pattern there that's meant to represent the fuse, that in the old days when we originally came up with this idea of fuses, it was essentially something along the lines of a very thin piece of metal. And that very thin piece of metal, when the current got too great, would actually melt and intentionally disconnect the circuit. But because it would intentionally disconnect the circuit, then the current would stop flowing before it melted any of the thicker wires. And so that fuse was kind of something that was used to break first so that it didn't melt anything further from there. We now use a little bit more advanced technologies in a lot of cases and use circuit breakers, but it's the same basic idea. It's something that is meant to be triggered by high amounts of current, and it will automatically break the circuit when the current gets too high. But with circuit breakers, there's also a button feature that will allow you to reset it. Whereas fuses, it's actually a piece of metal that melts, and so they need to be replaced with something else. But either way, whether it's a fuse or a circuit breaker, we tend to represent it with that same symbol that we would use for a fuse. A ground is something that we would need to connect to our electric circuit to provide another outlet for lots of excess charge. So if there is some kind of malfunction with the circuit and we build up lots of excess charge, we need some way for that to get safely directed into something that can absorb lots of energy, like the ground. And so to represent a ground connection, we just show something that looks a little bit like this. And so that's a wire that leads down, and those extra horizontal lines that get smaller and smaller represent the current that's going into the ground. That's what that symbol is representing. With an understanding of the circuit symbols, we can then use those to draw simple pictures of the two basic kinds of circuits, because there's a big difference between what we call a series circuit and a parallel circuit. So first off, in a series circuit, the electrons in the current, they have only one path that they can follow. So if any part of that path gets cut, the entire circuit is going to stop. The current cannot flow. And we also know that each electron must pass through all of the loads. So a simple series circuit we could draw maybe like so. So I'm just going to draw mine with a simple single cell and then some resistors to act as the loads. So I can draw my cell and then a resistor, and then I'll maybe have my circuit come down and I'll draw another resistor. I'll have it come over here and I'll draw another resistor, and then come back around to my original cell. So that is just a simple series circuit diagram where we've got one single source, we've got some connecting wires, and then we have three loads, three different resistors that our current's going to pass through. And because there's really only one path that the electrons can follow, each electron in that current must travel through each of the resistors. It must pass through all of the loads. But why this can be a little bit tricky is, as I said, if that path is cut off for any reason, then the entire current's going to stop flowing. And so one common example that we can state is old Christmas lights. And I specifically say old Christmas lights because nowadays most Christmas lights that you would buy have corrected this, and they don't use series circuits anymore. But a lot of them in the old days were designed based on series circuits. So all of the light bulbs were all connected together in one big series. But what would happen is often one of those light bulbs would eventually burn out. And when it burns out, that breaks up the circuit. And so if any one single light bulb in your entire Christmas display burnt out, it would cut off the power to all of your other light bulbs. And so you'd get none of them lighting up. Nowadays, though, they're able to construct Christmas lights in parallel circuits, which works a lot better because even if one bulb burns out, that's the only one that will burn out. All the others will continue to still go. And then what makes a parallel circuit different is that it gives the electrons different paths that they could possibly follow. So that means each electron will actually only go through one load and then return to the original source. So I'm going to draw a simple situation once again, and I'll just use, again, a simple cell and then some resistors to represent the loads. So if I have my cell, I might have my electrons that go all the way through and go through this resistor and go all the way back around to the source. But maybe there's another path they could follow. Maybe there's a different path they could take here and go through this resistor and then back around to the source. Or maybe there's a path that they could take over here and go through this resistor and go back around to the source. So in that case, each electron will actually only go through one of those loads each and then all the way back around to their source. And what's nice is even if one of these was, let's say they were all light bulbs instead of just resistors, if one of them burnt out and broke up that single path, we would still be able to get current flowing through the other two paths. In other words, the other two light bulbs would not burn out. And so for examples, really this is pretty much everything else in our everyday lives. And so in some simple cases, like things that might just be battery powered, they might follow simple series circuits, but the vast majority of the electrical appliances that we deal with in our everyday lives are actually running on parallel circuits. And so that's why when we plug different things into the same outlet, they are still able to run even when one of them is switched off or one of them dies out, because they're on separate or parallel paths. We're going to revisit this in class, talk about it in a bit more detail, and I'll also show some visualizations or some simulations of how these two different types of circuits work.